Alright, so we're going to look at this loaded beam, and this is the separate video we're going to look at for it. We're going to look at the moment calculations. We've got a reaction force at pin A in the y direction, reaction force at pin B in the y direction. We have a 35-pound present, that's a nice present, sitting on this beam, which then is 3 feet away from our pivot point A, and the total beam itself is 10 feet. So we want to know how much force is being applied there, and how much of that 35 pounds is being supported by these two reaction forces. So what do we got to do? We're going to take A as the pivot point, and we have a moment at C and a moment at B. So we're going to look at these two moments. So the moment at C needs to equal the moment at B in order for everything to be in equilibrium. C is trying to push that clockwise, while B is pushing back counterclockwise. So moment is force times distance. So we got force times distance, and those two should be equal. So the force, we have the 35-pound present times the distance of 3 feet, needs to equal the force, so the reaction force at pin B in the y direction, times our 10 feet. So 3 times 35 gives us 105, which equals our reaction force at pin B in the y direction times 10. So therefore, the reaction force at pin B in the y direction is 10.5 pounds of force. So that's 10.5. So now, the sum of all the forces in the y direction need to be equal 0. So if we've got 35 pounds force going down, that means the reaction force is going the opposite direction to be the opposite of that. It's got to take 35 minus 10.5. So the reaction force at pin A should be 35 minus 10.5. So we've got 24.5 pounds of force, which makes sense. The weight is closer to this than it is A than it is to B, so therefore this should be supporting more of the weight. Altogether, that sum of those gives us back that 35.